Hello, and welcome to our discussion on sampling distributions. That's Chapter 7. Today we're going to talk about the definition of a sampling distribution and some of the verbiage that goes along with this discussion. So there are three things that we want to talk about: parameters and statistics, sampling variability, and then describing sampling distribution. All right, so let's talk about the difference between a parameter and a statistic, and then how we're going to represent those mathematically. A parameter is a number that describes some characteristic of the entire population. So the key word here is entire population. In statistical practice, the value of a parameter is usually not known. This is what we're trying to get at in this statistical practice, is what this value is, because we cannot examine the entire population. So in comes statistics, and with the attempt to determine what the parameter is based on a sample of the population. So we're going to define parameter as a characteristic of the entire population, and then a statistic is going to be a number that describes some characteristic, or that same characteristic, that's the parameter, of a sample of the population. So the value of the statistic is going to be computed directly from the sample data, and then statistics are used to estimate the unknown parameter of the entire population. And so we're going to identify mathematically parameter as this P, and then statistic as a P with this hat. All right, so let's go through some examples. We want to identify the population parameter, sample the statistic of each of the following. So the first is Gallup poll asked a random sample of 515 U.S. adults whether or not they believe in ghosts. Of the respondents, 160 said yes. So in this case, the population is all U.S. adults. The parameter is a percent of all U.S. adults who believe in ghosts. The sample is 550 U.S. adults, and the statistic is going to be the percentage of the sample that believes in ghosts. So it would be 160 divided by 515. All right, second example: to prevent pipes from freezing at 32 degrees Fahrenheit, Mr. Otten sets the thermostat in his Kirkwood cabin to 50 degrees. During the winter, Mr. Otten takes 20 separate readings of internal temperature. To determine how low the temperature gets, the minimum reading is 38 degrees. All right, so the population is all the times during the day. The parameter is the lowest temperature in the cabin. The sample is 20 separate readings, and the statistic is 38 degrees as the minimum reading. All right, so these are examples of population, difference between population and sample, and the difference between parameter and statistic. Okay, so this brings us to our first homework problem, 7.1.1. I'm going to have you copy this down. So you're going to identify the population parameter, sample, and the statistic for each of the following. So I'm going to leave this up for a moment. You can pause the video. And then I am going to move on. Okay. Number 2, sampling variability. What do we mean by sampling variability? All right, so population distribution gives the values of the variable for all of the individuals in a population. Typically, we see some sort of bell curve or some normal distribution. Now, there can be sampling variability based on the samples of the same population. They can yield different results. So we could have in the population a normal distribution, but when we take samples depending on their size, we might end up with graphs that don't look normal. All right, so it could be skewed one way or the other. I could have multiple modes. So that's called sampling variability, because we're taking random subsets of the population. Those subsets are smaller, and depending on their size, we might end up with a greater degree of variability in that sample. All right, so population distribution gives the values of the variable for all individuals in the population. Now, a sampling distribution of a statistic is the distribution of values taken by the statistic in all possible samples of the same size from the same population. All right, so what we're going to do is we're going to designate, say we have a population of 1 million. We're going to take samples of 1,000, and we get some parameter p based on that sample, or some value that's associated with the parameter, mean value, and then we're going to end up with some sampling distribution. All right, so let's take a look at what this might look like in an example. So sampling distribution, again, of a statistic is a distribution of values taken by the statistic in all possible samples of the same size from the same population. So let's say we had 200 chips, 100 red and 100 blue, and then we created multiple samples of a count of 20. All right, so population, so now this is a population distribution, not the sampling distribution, gives the value of the variable for all individuals in the population. So we said we had 100 blue and 100 red. The individuals are the 200 chips, and the variable is the color. So now we're going to talk about the sampling distribution, move into the sampling distribution. So we're going to take a sample size of 20 of the chips, and then we're going to take a look at what that looks like in the different samples. So I have my parameter here is 8 out of 20.4 for the first one, and then the next simple random sample of 20 I have 11 out of 20, and the third I have 13 out of 20 that are red. All right, so you can see there's some variability because we're not sampling the entire population from each sampling set of data. First one, 12.8, second one, 9.11, third one, 7.13. So my parameter value is going to change based on each sample, and I'm going to end up with something that looks like this. So I take my parameter, and then I'm going to plot it here in its sampling distribution. The sampling distribution displays the collection of all values of p, should be p with a hat, the sampling statistic from all possible samples of the same size. In this case, we are using a sample size of 20. All right, so population distribution describes the individuals in the population. The sampling distribution describes how a statistic p varies in many samples from that same population. All right, so we're going to go back. We selected 20 chips 35 times, and then we populated the parameter here on this number line, and the results are below. So we had 20 colored poker chips again, put in a bucket, 100 blue, 100 red. Again, we randomly selected 20 chips, and we did this 35 times. And then the value p that we got for the parameter, then we're displaying that here as a dot, and then we're stacking those dots. So we want to describe the shape, center, and spread, and the outliers. All right, so the shape is symmetric. There's a single peak at 0.5. Center, the mean of the data collected below is 0.499. The spread is the standard deviation, 0.112, and there are no outliers. All right, so this brings us to your next homework problem, 7.1.2. Simulation software took 500 samples of the 200 chip experiment and recorded the graph below. So is this the sampling distribution of the statistic? Describe the distribution, shape, center, and spread. Approximate. If the teacher claims half of the 200 chips are red and you get a result that's 17 out of 20 chips that are red, what can you conclude? All right, or what might you conclude? So I'm going to leave this up here for another moment, and I'm going to move on to our last part of the discussion. So please copy this down or pause. All right, so describing sampling distribution. Last part of our discussion and our discussion about what sampling distribution is. All right, so what we want to do is we want to use a statistic to estimate a parameter. And as part of that process, we want to figure out how trustworthy that statistic is. So we take a look at some sampling data, and now we need to figure out how well the sample proportion of red chips estimates the population proportion of red chips, where we know that the population proportion is 0.5. All right. So in this case, we see that the population parameter and the statistic are much different. So an unbiased estimator in the graph is a statistic used to estimate a parameter where the statistic and the parameter are both very close to each other. So an unbiased estimator, a statistic used to estimate a parameter, is an unbiased estimator if the mean of the sampling distribution is equal to the true value of the parameter. It means it's unbiased. There's no difference between the two. All right, so let's take an example. Mr. Otten's stats class conducts a sampling distribution of student heights. Each sample size is 4 students. Here's an example of one of the samples, and the results are shown below. So sample 62, 75, 68, 63. Sample mean is 67. Sample range is 75 to 62, so it's 13. And then below is the list of the actual heights in the class. The actual mean of the class is 66.07, and the range is 21 inches. All right, so can we conclude that the parameter and the range are unbiased estimators? So here is a look at a bunch of sample means of n is equal to 4, and we end up with a center mean of 65.67. And we have a range center mean is 10.2 inches. So the mean of the ranges is 10.12, and the mean height is going to be 65.67. All right. So the conclusion we're going to draw is the sample mean is an unbiased estimator because the actual mean 66.07 and the sample mean 65.67 are very close. However, the sample range is a biased estimator because the actual range is 21 inches, but the sample range mean, the mean range of the samples, the sample data is going to be 10.12. Okay? All right. So let's talk about another example. How many people watch Survivor? The above represents 1,000 sample survey results, where in green the sample size n is 100, and in orange the sample size n is 1,000. What can we conclude? Well, what we can see is that the variability in the sample proportion is reduced, and the parameter typically better represents or is an unbiased estimator of the population proportion. All right, so we can conclude that the larger the sample size, so in the right-hand side, the closer or the smaller the range of p that approximates the population mean. Okay, so as we increase the value for n, this variability decreases, and the greater likelihood is that that parameter is going to represent the actual population proportion. Okay. So the variability of a statistic describes the range spread of a sampling distribution. The larger the value of n, sample size relative to the population, the smaller the variability. And so the example was the larger sample size for surveying percent of people who watch Survivor. So 1,000 versus 100 led to less variability in the sample results. We can look at this in terms of some bullseye. We have high bias, where the actual values are not on center or do not accurately represent the mean, but low variability, they're all congested together. low bias, meaning they're not representing the true mean, and high variability, meaning they're scattered. I have high bias here, they're not accurately representing, and high variability. Okay, the low bias would mean here that they're all represented around this mean, and so the mean value is going to be, of these samples, is going to end up being close to the population mean. And ideally what we want is something where all of the values are in the center, there's very low bias and very low variability, and we get that with a high sample size. Okay, this brings us to homework 7.1.3. Graph above left shows a distribution of interval times between eruptions of Old Faithful geyser. The graph above right shows a sample median of 500 simple random samples of 10 intervals, the mean of which is 73.5. And so you're going to answer these questions as a sample mean and unbiased estimator. Suppose the sample size were 20, not 10. How would that affect the graph to the right? And then describe the shape of the sampling distribution. Explain what it means in terms of overestimating or underestimating the population median. All right, that brings us to the end of this discussion. Please pause this if you haven't copied the homework assignment down. Thanks very much for joining. Come back. Let's talk when we talk about next section, sample proportions.